Hey, this is Kyle, and I'm going to be talking about two different methods we can use to find the constants of a relationship that's given in our book. And we're going to be finding these constants just by using, as if we're just using experimental data. Since I'm not actually performing an experiment, I'm going to simulate having experimental data using Python. So the first step is I want to import any libraries and functions I'm going to need to do this. So first, I'll import NumPy. Next, I'm going to need the minimize function, so that would be in scipy.optimize. And I want, like I said, I want the minimize function, and that's going to be used when we are doing the least squares method. That's all the mathematical functions we'll need. Now I'm just going to import the stuff I want for graphing. So first, I'll import plotly.io, which will allow me to make changes to the default settings of my graphs. And I'm importing this because I like a dark background to my graphs, so like I said, I can make changes to the default settings, so I'll change the background to be dark. Next, I will import plotly.graphObjects, which will allow me to use the the graphing mechanism I want, which in this case is going to be a 3D scatter plot. Let's go. And next, I will import the ability to actually make the subplots, so I can actually put the plots on my set of axes. So from plotly.subplots, import make subplots, and let's run this. So we got an error here. I believe it might be templates, not template. There we go. Next, I will define some of the variables, the dimensionless number, Reynolds number. For our relationship, Reynolds number only works, or the relationship only works if Reynolds number is from 2,000 to 35,000. And like I said, I'm going to simulate having experimental data, so we're going to do numpy.random. We're going to generate data. Random.uniform. So we can give it a range. We'll say from 2,000 to 35,000. We want 100 data points. And I'm going to do the same thing for Schmidt number, except that we know the relationship only works if Schmidt number is from 0.6 to 2.5. And we also want 100 data points for that. And finally, we have the Sherwood number, and that's defined, the relationship is defined in our book, and it's 0.023 times Reynolds number to the 0.83 power times Schmidt number to the 0.44 power. And like I said, this is the relationship, and we're actually going to be solving for these constants here. But the reason we're creating data with this relationship is so we can modify experimental data that we would get. And with this experimental data, we want to have it have a 10% error. So we're going to do numpy.random, and this time do a normal distributed data set, and we can set the center of our data set to be the defined Sherwood number we have, with a standard deviation of, like I said, 10%. So set that equal to 0.1 times our defined Sherwood numbers. Let's check for errors. Look good. Alright, so now I'll talk about the method of linear regression we're going to be doing. that's our first way of figuring out the coefficients. And I thought this would be easier to explain using pen and paper rather than Python, so I wrote it out and scanned in a PDF. So we're going to be doing linear regression with the Penrose pseudo-inverse method to find our constants a, b, and c in this relationship here. So as I said, it's the Sherwood number equals constant a times Reynolds number to the b power times Sherwood number to the c power. So the first step in this linear regression method is taking the natural log of both sides. And after we take the natural log of both sides, we simplify it so it's equal to the natural log of the Sherwood number equals constant a plus b times the natural log of Reynolds number plus c times the natural log of Schmidt number. Next we want to make a design matrix. So the design matrix kind of follows this right side of the equation here. So since this is constant a, we want this to just be solid ones, this whole first column in the design matrix. And the next column of the design matrix we want to be the natural log of the Reynolds number for all our data points. And the next column we want the value to be the natural log of the Schmidt number for all the for this column for all the data points we have. And then our parameter matrix is going to be our constants, so constant a, constant b, and constant c. And just like the equation, it's equal to the natural log of the Sherwood number. And for ease, we're going to call the design matrix x, this parameter matrix b, and our result matrix, Sherwood matrix y. Then we can modify this equation we have here. As long as we multiply the same thing on both sides, we're not actually modifying the equation. So first thing we're going to do is multiply the transverse matrix onto both sides. And this kind of simplifies down the left side. It makes this an easier matrix to work with. And once we have this multiplied onto both sides, we want to isolate b. And to isolate b, what we're going to do is we're going to multiply the left side by the inverse of this matrix that is multiplied by b. So if we do this, we end up having an identity matrix over here, because it's the inverse of a matrix times that same matrix itself. And multiplying any matrix by an identity matrix will keep it itself. So now we have isolated b on this side, and as I said, since we multiplied that on the left side of the equation, we have to multiply it on the right side. So now we have our matrix b, which is our parameter matrix, is equal to the inverse of the design matrix transversed times the design matrix, and then multiplied by the design matrix transverse times our result matrix of our natural log Sherwood numbers. And this is the relationship we can use to solve for a, b, and c. So I'll go back to Python now. And as I said, first we want to make a design matrix. So we're going to use, we currently have our variables as just one-dimensional arrays, and we want them to be the columns of a 2D array. So first we're going to do np.column stack, which will create the 1D arrays and make them columns in a 2D array. So our first column, we want to create an array of ones that is the same number. It has the same amount of ones as the amount of Sherwood experimental data numbers we have. So what we're going to do here is create an array of ones like, array of ones like the Sherwood experimental data we have. And then our second part of our columns of our design matrix is going to be the natural log of Reynolds numbers. So np.log of Reynolds numbers. Our third column is going to be the natural log np np.log of the Schmidt numbers. And then since we want this to be an array, I'm going to enclose it in brackets. Make sure there's no errors here. Okay, we're good. And so that's our design matrix. So now if we go back and look at this, the design matrix relates to our parameter matrix from this equation we ended up solving for. And then also this matrix that we already have, the Sherwood numbers. So now I'm ready to just have a parameter matrix, and I called that B. So like I said, it's equal to B is equal to the design matrix transverse times the design matrix, and the inverse of that times the design matrix transverse times our matrix Y. So we can see that over here by just saying B is equal to, let's see, B dot an algebra. So we're going to need to take the inverse of the matrix, so that's in the numpy.linear algebra and inverse. Inverse. And that takes the inverse of the matrix I enter here, so we want to take the inverse of the transverse times, and times for matrix is the @ sign, times the normal design matrix. And then we want to multiply this by the transverse of the design matrix, so we'll do that again. And we want to multiply it by the matrix we have of our Sherwood numbers, so natural log np.log of the Sherwood, of our experimental Sherwood numbers. Now we can get rid of this. Alright, so now no errors, so let's take a look at what B is. Oop, shift enter. So we can see that B is an array of our parameters, however this first one looks a little funky. And that's because when I was talking about B, I said the first element of B was constant A, when that's true, but that constant A didn't take into account that we took the natural log of both sides. So the first parameter we're actually going to need to find by doing e to the power of what the array returned to us. So we'll do np.exponential, and as I said, the first element of B, shift enter. So we can look at these numbers now, and these are our parameters. So A is 0.022 using this method, and that's pretty close to the 0.023 that the book's definition has. B is 0.8322, which is also very close, and C, which is 0.466, which is also reasonably close to what the book has, 0.44. And this makes sense that they're a little bit off since we're using experimental data. Now we're going to do the second method to find A, B, and C, and that's the least squares. So for this, we're going to define a function. I'm going to call that, sum least squares. So that's the method of this way to find A, B, and C. This is going to take in the parameters A, B, and C, and we're going to give it our initial guesses eventually. So as a part of this, we want to just find the difference between our experimental data and the actual data that the defined relationship gives. So we're going to return np sum we want to minimize the sum of all of the data points difference, so we're going to take the sum, and first have our experimental data, then subtract our and we're eventually going to square this, as in the name, it's the sum of the least squares. So I'll put a parentheses there and here. So we have our experimental data, and we want to subtract our data from using the the defined relationship. So that's going to be the first element we feed to this function, times Reynolds number, times the times the Reynolds number to the power of the second element we feed this function, times the Schmidt number to the power of the third element we feed this function. And as I said, we want to square this, so we want to find the sum of the lowest sum of the squares. So raise this to the second power. And no errors, so it looks good. So now we want to call on this function with our initial guesses, and not just call on it, we want to minimize it. So we're going to do, and that's why we imported the minimize function up here. So minimize. And as we can see, minimize takes in a function, and the function is obviously the function I made to do this. And our initial guesses, so it's an array, and we'll use the numbers that the book has for the constants in this relationship as our initial guesses. So 0.023 for A, 0.83 for B, and 0.44 for C. Shift enter. And as we can see, this minimize function returns its estimates for our A, B, and C values. And our A value estimate is 0.014, which is a bit off, but like I said, this is just an estimate. Our B value is 0.87, which is pretty good, a lot closer. And our C value is 0.51, which all of these numbers are in the same vicinity as the numbers we know to be correct. And this makes sense that there's a little they're different because there's going to be errors. We're using experimental data that is 10% varied from the perfect Sherwood numbers, and any error that is involved with the method we used. Alright, and that's it for the two methods to find A, B, and C, and I will come back and talk about graphing our results to show them visually.